Right, this video is a revision on Newton's laws of motion. Okay, the most important thing you need to be able to answer, right, okay, is when to use which law. Okay, let's start with Newton's first law. For Newton's first law, okay, when is it the situation that we can recognize, okay, that Newton's first law applies, right? Okay, so this is when you see that there is no change in state of motion. Okay, what does no change in state of motion mean? Right, okay, it means that either, right, okay, the object, if it is not moving, then it will not start to move. So when an object is stationary. Another case can be when if the object is already moving, okay, then it must be moving with constant velocity, right? Meaning constant speed in the same direction, right? Okay, so in these two cases, right, either stationary or constant velocity, right, we can see that it would mean that the acceleration of the object must be 0. Okay, and what does having 0 acceleration mean? Right, okay, then it would mean that net force acting on the object must be 0. Right, okay, so whenever therefore we have an object that we see, okay, not moving or constant velocity, right, okay, it would imply for us acceleration is 0, and that would tell us something about the way the forces acting on this body combine together. They must combine together to give a net 0. Okay, example. Okay, if I have an object, okay, of mass m, and if it's tied on a string, okay, and dangled on the ceiling, okay, then the free body diagram is going to look like this. We have upwards tension, we have downwards the weight, right? So since the object is not moving, it is stationary, right? Okay, then it must mean that Newton's first law applies. Okay, and therefore net force acting on it is 0. Okay, then it will imply that tension, the upward force, must be counterbalanced exactly by the downward force. So this will give us an equation, okay, to be formed based on net force is 0, and from this equation we can go on to solve for any other unknowns. Okay, so this is the case of Newton's first law, right? Okay, when we can use Newton's first law. Okay, so move on, we talk about Newton's second law. Okay, so Newton's second law will be when in the situation for the given object that is going to be a change in state of motion. What does change in state of motion mean? So it can mean that the speed is changing. So either speed up, slow down, or it can be changing in direction. Okay, so all this we can see that it tells us that it is its velocity is changing, right? Okay, and if the velocity is changing, then we can also say that the object has an acceleration. Okay, acceleration A. So since acceleration okay, compared to just now, right, okay, is 0 acceleration, okay, but now for Newton's second law, right, okay, we're dealing with the object has an acceleration. So what does it mean about the forces acting? Since we have the acceleration, then it must mean that the product MA is non-zero. Product MA is non-zero, okay, and therefore the net force is non-zero, right? Okay, and net force is given is magnitude of the net force is given by the product of the mass multiplied by the acceleration, Right, okay, so this is Newton's second law. Let's see an example. Okay, so let's say I again have the object that is being pulled by a rope, right? So upwards tension. Okay, again, downwards we have the weight, right? Okay, but say the rope is pulled by a larger force than just now, so my object is going to accelerate upwards. Okay, and thereby also, since movement is upwards, okay, and if air resistance is not negligible, there's going to be a downwards air resistance opposing the upwards movement. So in this case, if net force, right, it will be given as a combination of these three forces acting on the body. Okay, so when we deal with Newton's second law equation, right, net force equals to ma. Very often Newton's second law, we just refer to it as the net force equals to ma, right? Okay, but when we apply this Newton's second law, okay, the idea of it is that we look at the left hand side, okay, in as an expression, right, to give us the net force, right? Okay, so here in this situation, I have three forces acting, okay, and the expression of how these three forces combine together, right, knowing that the acceleration is upwards, okay, then it must mean that the upwards tension, okay, must have be bigger than the combination of the two, such that I can end up with upwards acceleration. So therefore, the combination of the three forces must be in this form, right? T minus W minus the air resistance, okay, and the unbalanced amount, the leftover amount, right, okay, must be such that T is bigger than the other two forces combined, and then we have a remaining value of the force which is upwards. Okay, and on the right hand side, okay, will be the product of mass times the acceleration. Right, okay, so from here we use the Newton's second law to again form an equation. Okay, and after forming the working equation, this will allow us to work to substitute and then solve for whatever unknown value that we need. Right, okay, so this is Newton's second law. Right, we will use it, okay, whenever we observe in the situation there is a change in state of motion, meaning we look out for whether, right, okay, there is an acceleration. Oops. Okay, when there is an acceleration happening. Okay, so alright, okay, so this is Newton's second law, right? First law and second law, right? Okay, the Newton's third law now, right? Okay, so Newton's third law, this law is a little bit different compared to the Newton's first and second law, right? Okay, because we can see that Newton's first and second law, okay, allows for us to form equations and then we solve for unknowns, okay, by looking out for whether there is acceleration or not. Right, okay, but Newton's third law, okay, the nature of it is slightly different. Newton's third law, it serves to give explanation. Okay, to forces, and the idea that forces arising in pairs. So meaning whenever one force arises, okay, that is actually another force that happens to be created, right, okay, to arise together along with the first force, okay, and we call this, right, okay, you must know by now, wait, right, okay, that the other force is, these two forces, okay, we call them action-reaction pair. Okay, so action-reaction pair of forces. Right, okay, so my short form here, I'll just call this ARP. Right, let's use a simple example of a man, maybe a man standing. right? Okay, so for the guy standing, we know that there will be a downward weight acting on it, right? Okay, and then at the same time there is also he's standing on the floor, right? Okay, so there will also be a upwards normal force, okay, acting on him, right? Okay, so are these two forces, do these two forces form an action reaction pair? Alright, okay, so we let's evaluate this. Alright, okay, so let's look at the first force of weight. Okay, and we need to look at what exactly is this force that we refer to as weight. Right, okay, so this force, if you look at what actually it is a type of gravitational force, and it is exerted by Earth on the man. Right, okay, so let's call this force number 1. So now if we want to look for its action reaction pair, okay, then the action reaction pair, alright, okay, of this force number 1, okay, it must be firstly also another gravitational force. Right, okay, so what its action reaction pair, right, the ARP looks like, it must also be a gravitational force, right, okay, but acting by, right, okay, so here, okay, what we will need to do, what we can very easily help us identify which what the other force is by looking at the two bodies that are interacting. Right, okay, so if the first force is by Earth on man, then the second force must be a force which is also involving these two interacting objects. Right, okay, so the Earth and the man, okay, you need to swap them. Right, okay, and we also take note that, okay, the nature of the force is the same, so both are gravitational force. Alright, okay, but Earth and man, you must swap them. So it is force of the same type, same nature, alright, okay, but acting on the different bodies in the interacting pair. Okay, so let's call this second force F2. Alright, okay, and let's also take a look at the normal force and try to identify its action reaction pair. Alright, okay, so for the normal force, right, okay, so on the man first, okay, for the normal force acting on the man, okay, let's call this N1. Okay, so the force N1, okay, therefore is of this type of force. It is a contact force, right? Normal force is a type of contact force, and then it is acting by, okay, so in this case it is the man standing on the floor and the floor supporting the man. Okay, so this is a contact force by floor on the man. So if we want to look for its action reaction pair, then we must be also looking for another force of the same nature, so therefore also a contact force, okay, but by, okay, so here the floor and the man, we need to swap them, right? So between the two interacting pairs of object, right, if A is acting on B, B is also acting on A, so here we swap them. So again, right, okay, the same consistent pattern, okay, in the way that Newton's third law applies, right, okay, the type of force is the same, and the two bodies that are interacting, okay, they are exerting a force mutually on each other. Okay, so this, let's call it N2. Right, okay, so if I would to draw this into a diagram, okay, then what object? The object that is experiencing N2 will be the floor. Okay, so then my diagram, okay, will look like this on the floor. The N2 is by the man pressing down on the floor. right? Okay, so these are the two forces, N1 and N2. Okay, so now if I were to continue this example and then we summarize a little bit, all right, okay, on the Newton's third law. Okay, then Newton's third law, okay, we can see that there is this three things, okay, that we need to look out for, right? Okay, and the three things that we need to look out for, okay, answers for us, right? Okay, that in the action-reaction pair, the two forces are always, okay, number one, always of the same nature, meaning of the same type, right? Okay, so if one is gravitational force, then the other one must also be gravitational force, right? Okay, if one is a contact force, then the other one must also be a contact force, etc. Right? Okay, criteria number two, the two forces will always be of the same magnitude. Okay, there is this mutuality in the way that the two objects interact, so such that the action-reaction pair always, okay, will be of the same magnitude. Okay, and then number three, the two forces are always acting on the two different bodies. Right, okay, so meaning A on B, there will be a force that is by A on B, and then the other force will be by B on A. Right, okay, so once you examine these three criteria, and if the forces match all of these three, okay, then you can be certain that the two forces form an action-reaction pair. Right, okay, so now if we go back to just now's this man, right, okay, this example here, let me try and copy and paste. Okay, so now classic example, right? Okay, many students would think that if my weight, if let's say it is 600 Newton, right, and if the man is stationary, right, okay, then it becomes my Newton's first law situation, right, okay, where net force is zero because it's stationary. Okay, so therefore net force is zero, okay, and therefore outward force equals to downward force. Right, okay, our equation formed is this way, and therefore it leads us to the conclusion, right, okay, that the outward force, the normal force, must be equals to the weight, and therefore must be equal to 600 Newton. Right, okay, and because one is upwards, one is downwards, right, okay, opposite direction, same magnitude, right, the opposite direction and then same magnitude, okay, and therefore it leads many people to think that these two must thus, right, okay, be an action-reaction pair, right, okay, but now let's look at the three criteria, right, okay, to check this as a conclusion, right, okay, so firstly, okay, are these two forces, are they of the same nature? Okay, so one is normal force is a contact force, weight is a gravitational force, right, okay, so in this case they are not of the same nature, right, so our criteria number one, okay, is not met, they are not of the same nature. All right, okay, so now if we check on the criteria number three, which is acting on the two different bodies, okay, so here we can clearly see that normal force is acting on the man, the weight is also a force that is acting on the man, so both forces in this case are both acting on the same body, so criteria number three is also not met. Right, okay, so therefore well, we do not need to examine it further, right, okay, we can already conclude that they do not this normal force and the weight, they do not form the action-reaction pair, right, okay, but let's continue to look at number two. Okay, so number two, if the weight is 600 Newton, Okay, does it mean that the normal force must always be also 600 Newton? Right, okay, the answer here is also not always true, right? Okay, because the weight is given by mg, so long as the mass does not change, the gravitational field strength does not change, my 600 Newton of weight is not going to change. Okay, but the normal force is going to be able to change, right? Okay, let's talk about this situation. Right, okay, let's maybe talk about the same person, right, the man, right, okay, and then if I tie him up, alright, okay, to a rope, okay, and then tie the rope to the ceiling, right, okay, so then for this person over here, right, okay, the forces acting on this guy, right, okay, I will still have the weight, okay, pulling him downwards by earth, okay, I will still have the normal reaction force, okay, by the ground, right, okay, but now I also have a third force, okay, which is the tension in the rope, okay, that is supporting him, that is pulling him upwards. So in this case, I will have two forces upwards, one force which is acting downwards. So if the man is still stationary, okay, then, right, okay, by the fact that he's stationary, we're going to then be able to apply Newton's first law. The total outward force must be counterbalanced by the total downward force. So T plus N is equals to W. So here we can very easily therefore see that the normal force is equals to W minus T. So the normal force is now going to be a value that is lesser than 600, while the weight of the guy, right, okay, of the person is still 600 Newton. So this, right, okay, demonstrates that the normal force, right, need not necessarily always be equal to the value of the weight. Okay, that happens only if, okay, the man is stationary and also no other forces acting on him, right? Okay, another case in which very easily we can also see that the normal force can be a value that is different from the weight. Okay, it can be the case when, say, you are trying to jump, right? Okay, so imagine yourself, if you are trying to jump, okay, this is my best drawing of a person, actually not bad, trying to jump. So when you're trying to jump, you will be using your leg muscle to exert a force, pushing, right? Okay, but you think about it, you are actually pushing on the ground, right? Okay, so but when you are pushing on the ground, right, when you're pushing on the ground, so force by man on ground, right, okay, that is you pushing harder onto the ground. Okay, then at the same time, action reaction pair, the ground will be pushing back on you, right, okay, with a normal force, okay, that is equal in magnitude to this force that you are pushing against onto the ground, right? Okay, so we have therefore normal force, right, okay, that is bigger than usual, right? Okay, so let me erase this so that we focus only on the forces acting on the man. Alright, okay, so the weight is still downwards, okay, but I have the normal reaction force, okay, by the floor on the man is upwards, okay, and since if we do manage to achieve to jump upwards, it would mean that I will have an upwards acceleration, right? Okay, so in this case, by using Newton's second law, since my acceleration is upwards, okay, then it would mean that for the net force, right, one up, one down, my acceleration is upwards, it would mean that my normal reaction force must be bigger, so that I can have some leftover unbalanced force that is possibly upwards. So therefore N less W to give the product MA. Okay, so in this case, if you make N the subject, okay, then you will see that N is going to be a value that is bigger than W, right? Okay, such that there is this unbalanced part of the outwards normal force, right, okay, bigger than the W, and the remaining part of it, right, okay, can give the outwards movement, outwards acceleration, right, okay, and you are able to jump off the ground. Okay, so this is a to show you that therefore for the normal force, okay, for the criteria number 2, right, okay, it is also not necessarily always equal, right, okay, to the weight's magnitude. Right, okay, it's normal force is actually a force depending on how hard the person is pushing on the ground, and then the ground is pushing back on the person equally with that same pushing effect. Okay, so it not necessarily is always equal to the magnitude of the weight. So therefore, even criteria number 2 is not always obeyed. Right, okay, so and thus it's very clear, okay, for this kind of two forces, alright, okay, the two forces, normal force and weight, they do not form an action reaction pair. Alright, okay, there is a criteria number 4 over here, alright, okay, which I think everybody are very familiar, right, okay, so that they are opposite in direction. Okay, okay, which you can see was discussed just now. Alright, okay, so these are the 3 laws. Okay, so I will end my video here. Alright, okay, I will be making another video to show how these 3 laws apply to the question in 10-year series paper 2 2023. I think it's question 2. Alright, okay, so do look out for that video.